Okay, welcome to the lecture on computing the parsimony and likelihood scores on trees. The first part of this lecture that I'm going to give now will just deal with the parsimony scores. Um, so overall, to give you an overview, we have the character-based methods, and among those character-based methods we have parsimony, and then the two methods that are based on the likelihood function, that is maximum likelihood and Bayesian inference, that essentially computationally do the same thing when it comes to the bulk of their computations. So they're just evaluating the likelihood function over and over again. They're just essentially, from a computer scientist's point of view, using different search strategies. Okay, so this is what I just said. So with respect to the similarities, or why we are actually doing parsimony, is that the score calculations on trees, the way we compute scores algorithmically, are very similar for parsimony and likelihood. Um, so that's why we're actually starting with parsimony, because it's easier to understand as it is a discrete criterion, and then we're going to move over to likelihood. Also, both models of parsimony and likelihood assume that the sites evolve independently, meaning that if we can compute the score for one site, we can actually compute it for all sites. All right. Then there are more similarities. So, given an unrooted binary tree, how do we score it? So step one always is like that: we just randomly throw a virtual root at the tree to define an order of computations, right? So mathematically our trees are unrooted both for parsimony and likelihood, and but in order to be able to compute a parsimony or likelihood score, we need some rooting that determines an order by which we traverse the tree. So parsimony and likelihood scores are the same irrespective of the actual root placement, right? So regardless of where I place the root, I'll get the same parsimony score and the same likelihood score. For likelihood, of course, we're assuming that the likelihood model, the Markov chain, is time reversible. So if the model that we're using, the substitution model or the statistical model of nucleotide evolution that we're using, is not time reversible, then the above doesn't hold anymore. So we will get different likelihood scores for the very same tree, depending on where we place the root. So this is one part of the similarities. And then the second part, or set of similarities, is how we actually traverse the tree. So unfortunately, I forgot to duplicate the slide here. So basically, in step two, so after we've placed the root, we traverse the tree starting from the root to full sum vectors at the inner nodes that essentially summarize the signal coming from the subtree below that inner node. And in parsimony, we do that via operations on integers because we're essentially just counting mutations. And in likelihood, we're doing that via operations on floating point numbers as we're doing statistics. And then once under parsimony or likelihood we've reached that virtual root, we can then compute the overall tree score over there. Right. So let's look at this step by step. So first we are doing an arbitrary rooting of our unrooted binary tree topology. So we throw the virtual root in here, and then we just kind of pull up this virtual root to obtain rooted tree. So here's just like an alternative arbitrary rooting that we could also use for scoring this tree. Okay, so here's the slide I was missing before about the tree traversals, so I'm not going to repeat it here. Okay. So the next question is, how can we actually traverse and compute something on a binary tree, on a rooted binary tree? Well, we have three options. So if we walk along the tree, we can do something, some calculations essentially. The first time we visit a node of a tree, so this is called a pre-order traversal. We can do something the second time we visit a node, so this is called an in-order traversal. And we can do something the third time we visit a node, and this is called a post-order traversal. So I'm just going to show you the different traversal orders, right? So you start at the virtual root and start walking essentially along the tree, visiting all nodes and all branches of the tree. And so if we do pre-order traversal, the first time we encounter an inner node of the tree, we do some calculations here. So that's pre-order traversal. Then in-order traversal is like the second time we visit a node in the tree, we do some computations here. And then finally, we have the so-called post-order traversal, where we actually do some computations the last time we visit a node. So essentially here, what the post-order helps us to do is that we first descend into the subtrees, do our computations there, so here to the left and to the right, and then we use the results of those computations to compute something at this inner node here. So basically what we're doing is that we're conducting computations bottom up from the leaves toward the virtual root. So for parsimony and likelihood, we use post-order traversals, and this is, as I just said, that we calculate stuff bottom up from the leaves toward the virtual root. Okay, so here are some sequences for you, and here's how that works conceptually again for parsimony as well as for likelihood. So every time we visit an inner node for the last time in post-order, we fill vectors at the inner nodes that have as many elements as a multiple sequence alignment has sites. So in our simple example here, those will be 4 elements. And this kind of vector that we compute here summarizes the signal coming from the subtree that is located below the vector. So then we do that for the remaining inner nodes in our tree, also in post order. And then in the very end, we compute a analogous vector at the virtual root of the tree. And then, so what do those vector elements actually contain? So under parsimony, they contain a state set information. So what are the possible ancestral states at a specific position, let's say here. And well, for likelihood, this contains the likelihoods or the conditional likelihoods. So essentially, for each alignment site under likelihood, we have like 4 entries here that tell us what is the probability of observing an A given the subtree, of observing a C here given the subtree, of observing a G here given the subtree, and of observing a T here given the subtree. So this given the subtree means basically that we're computing a conditional likelihood. Right. And as I've already said, this is just visualized here now, the vector always summarizes the phylogenetic signal of the respective subtree that is located below the inner node. Okay, so now let's talk a little bit more about the parsimony criterion. Since it's a character-based method, it directly operates on the MSA, and it attempts to find the tree that explains the data with the least amount of mutations. Right? So we're just trying to find the tree that can explain the data or generate the observed MSA multiple sequence alignment data with using the least amount of mutations. So now the question is, well, how do we calculate a parsimony score for a given tree topology? So how do we calculate this least amount of mutations it is required to explain the data for a given tree? Right, so here's how parsimony works. We're given our multiple sequence alignment with the sequences here and our tree topology down here, and then we just kind of assign the sequences to the tips of that tree. And what we're actually trying to do in parsimony is that we try to find an assignment of sequences to the inner nodes of the tree such that the number of mutations is minimized. So here's a question for you to think about a little bit. So what could the inner sequences look like? So for instance, if you just try to do this intuitively by eye, you can see that here we have an A, here we have an A, here we have an A, and here we have an A. So this, the inner state here must clearly be an A. And then here we have an A or a G. So this at this position could be A or G. And then we have G or gap. So maybe we could put a G here. And then the same applies here. So at the third position we have an A here. At the other positions it's kind of less clear what we should put here, but because we have a T here and an A here, so this at the first position could be an A or a T, but we somehow also have to look at the other sequence, so the signal coming from the left part of the tree here. So maybe we better put an A here and count a mutation from A to T along this branch. So this is like the intuitive explanation of how parsimony score calculations work. And so basically once we have assigned those inner states, we can now just count the mutations on this tree. So here this is 1 because G is going to A. Then here this is actually 0 because we have 3 A's here, and then gap to G. So gap is actually, the gap is represented as an undetermined character state. So it could be either A or C or G or T. And so transition from A or C or G or T to G has 0 mutations. Then going from one inner state to the other, we just have a mutation at the second position here. So A is going to G. And then we're going from those two sequences are identical, so we have 0 mutations. Then along this final branch we have 3 mutations basically on the first, second and fourth position where those characters mutate to T. Right, so thereby we have the overall parsimony score of our tree basically by just summing up the mutations over the branches, and this is then 5, right? So the parsimony score of this tree is 5. And so it happens to also be the minimum score for this tree, right? Because we could have made some sort of random assignments here and could have, for instance, put, I don't know, maybe a G at this position here, or maybe a T somewhere here. So we could end up with a higher score for this tree if we kind of don't choose the ancestral sequences here at the inner nodes appropriately. Okay, so as I mentioned before, gaps are treated as so-called undetermined characters that are also frequently denoted as N. And so, as I said before, the interpretation is that N could either be A or C or G or T. Right, so this is basically a representation of our intuition, but we still don't know how to compute the score. So first we place a virtual root onto our tree. Now we have a rooted tree, and now what we do is that we, as I said before, then we conduct a post-order traversal to compute the inner states, inner state vectors of our parsimony tree. So how does that work? As I said before, we're just interested in being able to compute the parsimony score of single sites. And so that's what we're going to do here. In the first step, what we do is that we transform our nucleotides into bit vector representation, right? So we're representing them by 4 bits, and a bit is set if we have an A here, so we set the first bit, and if we have a T here, we set the last bit. And so, like, if we had a C, we would set this bit here, and if we had a G, we would set this bit here. So now what we do is that essentially those bit vectors represent a set representation of the possible nucleotide states. So what we do at an inner node is that we compute the intersection of the sets of possible states at the ancestor, and if this intersection is not empty, there is no mutation. So the intersection here of those two essentially set representations of nucleotide states is just like the bitwise AND operation on the two child vectors. So here we see that the intersection is not empty. This means that, well, no mutation has happened as well when going from the two children to this node here. And so the ancestral state at this inner node here is A. So once again represented as a set that is modeled by a bit vector. Okay. And so those 4 bits are just like one vector element, right? So this is this should be clear. And so the way we can think about this is that, well, our alignment has 4 sides overall, and so the entry of the vector here is 1, 0, 0, 0. And just as a side note, so under likelihood, what we actually store here are not bits, but floating point values. So under likelihood, we would store the conditional likelihood of observing A, C, G, and T here. And typically, the conditional likelihoods for C, G, and T will not be 0 here, right? Just because of, by design of the likelihood model. Okay, let's go back to parsimony. So let's look at this right subtree. Here, once again, we compute the intersection of the two nucleotide state sets to the left and to the right, and we see that it's empty. So this means that we need to count 1 mutation. Right? So we're counting 1 mutation plus 1. And then, since the intersection is empty, the ancestral state is actually the union of the two child state sets. So here we do not store the result of the intersection because intersection is empty, but we store the union of the two sets. So we say, well, here at this inner node, the ancestral state could either be an A or a T. We cannot really decide yet because we're kind of waiting for the information, for getting more information from the left part of the tree. So this is kind of the key trick of parsimony calculations. That's the only thing that you really need to understand, that we defer the decision whether this should be a T or an A to a later point in time. And that's why we store that as a set union. Okay, then we go to the virtual root. Basically, we compute once again the intersection of the left child vector here and of the right child vector here. We see that the intersection is not empty, so the overall score for this, the overall parsimony score for this alignment side is just 1. Okay, so here now we've computed 1, and then we can move over to the other sides of our alignment. So here's like a little exercise for you. What would be the score for the second, the parsimony score of the second column here in this tree? So if you look about it here, we have an A. If you look at it here, we have an A in here, so there are no mutations here. But here's a T and a G, so there's definitely 1 mutation here and another one here. So basically here the parsimony score is 2. We get to the next point, G, A, A, A. You can probably guess if there's only 1 G and otherwise A's that there is just like 1 mutation. And finally, we have G, gap, TG. So what is the parsimony score here? Let's have a look at it in more detail, because here we have this undetermined character state. So we say that it could either be A, C, G, or T as shown in our set representation. And so we move up here. We see that the intersection is not empty, it should be a G. And then we look at the other child node. Here we see that the intersection is actually empty. So this will be G or T. Then we go to the virtual root, take the intersection or the bitwise AND of those two vectors and see that it's not empty. So the parsimony score of the last side of the alignment is also 1. So we do this calculation here. And then as we're done, we just take the sum of over the per site parsimony scores and see that the overall parsimony score here for this tree is 5. Right. So here's an exercise for you. You should take your pen and paper out again and pause the presentation and try to calculate the parsimony score of this tree here. So assuming that you've done that, here's the solution. So the overall parsimony score of this tree is actually 6. Okay. Now let's look a little bit at some properties of the parsimony score. So what's the time complexity to score one tree? So this is something we're interested in computer science, just to figure out how long our calculations will take and what are like the main factors influencing execution time. So we have like a multiple sequence alignment with n tags and m sites, and what we need to do is, well, that we need to visit, if we have a given fixed tree, we need to visit every inner node once. And so we need to do n minus 2. We need to visit n minus 2 inner nodes and perform m calculations at each node. So basically our time complexity is big O of n times m. But the constant hidden in this big O notation is very small. So if you're not aware of the big O notation, this is something that we can discuss in the discussion meeting. So what's the space complexity? So we have the time complexity. The other thing we're always interested in is the space complexity. So how much RAM do we actually need? So to store the alignment, we need n times m times 4 bits, right? If it's like in some sort of compressed form. To store the ancestral nodes, it's the number of ancestral nodes times m, the length of the alignment, times 4 bits, because we need 4 bits per character. And then finally, we need to have some sort of score counter at each inner node. And this is basically just the number of inner nodes multiplied with 32 bits. So the space complexity of parsimony calculations is also big O of n times m. But again, the constant hidden in the big O notation is very, very small. So why am I doing this? Well, I want to talk a little bit about maximum likelihood. So maximum likelihood has the same time and space complexity, but the constants are much, much, much larger. And this is something you know, of course, because doing a maximum likelihood analysis does take so much more time than doing a parsimony analysis. Okay, then now here's kind of the classic transition to maximum likelihood, or why we actually need maximum likelihood. So because parsimony tries to minimize the number of mutations on the tree, it faces some problems on trees with long branches, right? So this here on the left-hand side would be the correct tree, and this tree here on the right-hand side would be the incorrect tree as inferred by parsimony, and this is due to this kind of long branch attraction effect, which can be somehow alleviated by maximum likelihood. Right, so there's this kind of very classic paper here by the, well, Pope of likelihood-based methods, Joe Felsenstein. So the settings under which parsimony recovers the wrong tree are also called the Felsenstein zone, after Joe, who, as you might know, has made numerous and very important contributions to the field, like the first description of an efficient method for computing the maximum likelihood score in a tree, and also the bootstrapping procedure. Right. And so now let's talk a little bit about likelihood. I will kind of take a break here and continue later on, but here's the introduction. So once again, we are given the multiple sequence alignment, and we're also assuming that we're given the tree topology, but this tree topology also has branch lengths. So unlike in parsimony where we don't care about branch lengths, here we do have branch lengths. Then we're also given a model of nucleotide substitution. So this could be Jukes-Cantor or GTR, so the general time reversible model of nucleotide substitution. And the other thing that we're assuming is that we can calculate the transition probability from a nucleotide state X to a nucleotide state Z after a time, or like for a branch length B. Right. And so here's the question that we're trying to answer. So what's the likelihood of this tree? How do we calculate the likelihood of this tree? So once again, as for parsimony, we place a virtual root onto this tree. We root it, and now here we have some additional labels. So we have our inner nodes here, but we also have our branch lengths allocated to each branch. And so the branch lengths correspond or show the mean expected number of substitutions per site in our alignment. Okay, so this is the end of the first part of this presentation, and then later on we'll figure out how to calculate the likelihood on such a tree.